And now we are recording to the cloud. I think Alyssa and Carla just joined. I hope we are recording to the cloud. And then here's our Thursday. This Thursday 18th, I think. So I'm gonna go on the share. I think I'm clicking kind of randomly here. Now we have a good keyboard. There's a different kind of keyboard. It has a wire. The other one had the little thing stolen. 5 people. Christina, good. And then Blake. All right. That thing is good now. So we're now recording, and I'm gonna okay, I'm going to comment. Come on. That's the time when we're starting. So July 18th, Thursday. This is the week before the last. We just had a good lecture yesterday. I can hear. Very good. Thank you so much. Can you also say a few words? Good morning. Good morning to you too.
Hi, how are you?
Okay, hang on. I think we don't hear you on account that I didn't do the test. So let me see. I don't think that my sound is coming to the right. Come on. Okay. Just a second. See, the first one doesn't come out. So try. One. Great. So can somebody say hello?
Hello?
Great, we can hear you now. It's excellent. Yeah. So 8:52 on Thursday morning, July 18. We have Elmar in here and a few people online. We are recording, and we need to get started. So I'm not logged into Gmail or Google Colab or something, but let me just try to do it. We might write notebooks today. Goal would be today not necessarily to write notebooks, but rather to sign in. The goal would be to calculate now instead of nominal. And calculate, so what was that again? The coding. And we go on the gmail.com. And then my password, let me see if I remember it. And then I'm in, and so if I do Google Colab, right here, it will take me to this thing where I'm going to start a new notebook, and that's fine. I have a new notebook, which might serve me well if I do anything. This is Zoom. This is all time. I'm going to reload, make sure I get the most recent time. It's 8:54. We're going to get started. So I'm going to go to our. I don't have the iPad connected, but I will because I have to write something today. Maybe I hope. C290, and let's see where we are. But first of all, if we click on the 17th, which was yesterday, you have the video. The video is right here, and it came out really well considering that we had some issues. One thing that I believe is good is that some materials have been left out.
We gotta wait in supervision.
Just show you more. Share computer sounds.
Okay, so I think Amy clarified the question. Is a superposition?
Very good. So we got this, and I hope you remember that there are some links over here. That this is a link from last time, so nothing new here. It's the same website, but this is a link to a interview, and these are the slides from yesterday. They are in PowerPoint. These are the videos that she tried to combine into the presentation. At the end, the stuff. Let me show you the slides. I don't remember if she did do the slides yesterday. So what am I doing here with this? Close. I'm going to say got it, and I'm going to create a slideshow, and it's going to be from beginning. So these are the things that she did yesterday. I hope things are coming through properly. She disconnected by mistake or by way of network being unstable. And as we went through these things, she wasn't able to cover it. And I think that's really good because that means that we're all looking forward, everybody, to the last lecture next week. So then there are some take-home activities. I don't know if she put them in or she put them afterwards when she sent the PowerPoint. And then this is the content that she didn't get to that will be continued in the lecture, a week from yesterday. Okay, so a week from, I'm gonna close this. A week from Wednesday, we are going to go. And I said, this is where the agendas. A week from Wednesdays, we are going to have this presentation, which means there's already content planned for the lecture on Wednesday. But on top of that, there's some stuff that you didn't get to. So hopefully we'll be more careful and more organized here, and we won't allow any kind of random act of sabotage. If that's what it was, happen. And hopefully we'll start on time and we'll do the right thing, and we'll get the last lecture plus the content that we didn't get to last week. So having said this, I click on what's due and I say you really should continue to aim for these things. So this week, week 5 deliverable, it's not yet due, basically. The super dense coding that we're going to start talking about today. There are 3 links over here that I think I showed on Tuesday, maybe, that we're going to explore now. I guess that's all I want to show from there. And I'm going to come back over here and I'm going to tell you that today being 18, I would like to click on the 12th. No, I'm going to click on 15. I'm not sure exactly. Let's click on 12. So, what I have to do, what I said I would be doing is finish that assignment with matrices, linear algebra, but there wasn't much to finish. If you go into the lecture before, which is 11th, then we have something meaningful about matrices. Where did I put the answers to them? If I click on the 20, that's a lecture. If you go on the 9th, that's also here. Where exactly did I put the answers to the linear algebra? Maybe 5th? No, I'm not sure where exactly I put it. 4th, yeah. So look, I put them in the past because I had empty space on those lecture notes, and I didn't get to finish 14. We have 18, so there are 4 more problems that I need to bring up. I mean, of course, you can do that by yourselves, but since I promise I'll do everything to make sure that you have some reference under the data over here, I need to put questions 15, 16, 17, and 18, I guess. And I didn't. But what I did was this is Friday, right? I put Friday, even though what we did was in fact discussed then, but then we visited on Monday. On Monday, our derivation was in a hurry, and it was fine except for one little thing towards the end of the lecture. And then I said I would probably need to recreate the derivation and post it over here so you can look at it. And even though this is listed on the Friday, actually I did this yesterday, which is after the days in which we sliced the circuit. See, on Monday we decided that the circuit that we should talk about is the one with the oracle for 0, 0. That means we put the card under the first position. And I started doing exactly the same thing. You do Q0, Q1, and there's just this at the beginning. You put 2 Hadamard gates and you get this. You also write down how Qiskit reports it. You add the x's, this is what comes out of it. So if you look at it, right, there are 2 qubits, each one is a superposition. Then if you want to take the tensor product, that means create a superposition of systems of 2 qubits. Then it's this, which is the same thing as above. Basically 2 X gates following 2 Hadamard gates that were fed with 2 white blobs are basically going to be the same. So I said same as above, and my next goal was to introduce a control Z. That's part of the oracle. It's 2/3 of the oracle. I wrote this down and I said that's part 1 of 3 for Grover. And you know at this point that what I'm doing is correct because we did check this with Qiskit. So I'm going to come back here and say I put this first of 3 derivations in Grover on Friday, so that on Monday we said we developed this notebook. We didn't develop it in class. I developed afterwards, but it's the one that says, well, maybe we did. I forgot. This is basically the way things look, and we knew after seeing this video, this notebook, that the result of this particular circuit is exactly the position where the queen is supposed to be, 0, 0, which is the first position. Okay, so now the notebook does not tell us how things proceed, but it tells us what the answer is. So at least we believe that this is the right circuit. And so I kept saying, this is what the state was at that position. I put two X's to finish the article. And then I show you how I proceed. And that's the end of that derivation. Then I had two Hadamard gates, and I said, please be careful, because this is the part that is the more time consuming, because I am going to apply Hadamard on every single qubit. But the new aspect here is that look what I did. I took the superpositions and I put them next to each other. I mean, there are only a very small and finite number of combinations. I know that it looks like this too much and it explodes, but actually there's just four possible cases, and that's the end of it. So I put them next to below each other, and then in a column, so to speak, in a matrix kind of thing, so that when I unpack them, I get these situations: white, white, black, white, white, black, black, black. So I can then cancel them. And look, there's black with a face followed by white. That's going to cancel with black, white. And I cancel them in red. And so exactly as I did in the booklet, I'm left with less. What am I going to be left with? I'm going to be left with two pairs of white blobs. And then I have black with a phase, white, which is the same as black, white with a global phase. Because we discussed how phases apply to systems of qubits. I can put it in front, on top, or on each one of them, either one. And so as I write them next to each other, I keep writing them the way they appear after cancellation, because I had 16 and now I have only 8. But then because I have 2 of each, and I start in the beginning to tell you that if I have n and m, and then I multiply each with k, then the probability stays the same. That's in the very beginning when we discussed how do you calculate probability. Then, because I have 2 everywhere, I can cancel them and keep only 1, which is this result, which, by the way, has been checked the next day in the notebook in the next day as this. So I'm saying 0, 0 for white, white. I'm saying 0, 1 for black, white, because it's reversed. And so I'm here at the point where preparation of state is done. I have an oracle, and I have just started dealing with a reflection circuit. So I'm going to go to the next lecture, which is on 16. And this is finishing the whole thing, since that concludes the proof or the check or the trace. In this class, we did in fact do this in class. The number one thing was, let's take slice by slice and be sure that we know what we expect. So when we do the derivation, which I tried in the video on Monday, and I did it perfectly up until the last minute when I forgot to put a face somewhere. And then we also stopped, by the way. So all these intermediary results are going to guide us. And so I came over here and I said, I'm going to put two Z's, because that's what I have, Z gates. And so this is how this works. And I'm finished and I get this one, which, by the way, Qiskit is reporting as this. And since I want to add another control Z, I am a little bit worried that this red line should have been right in front of a control Z. Maybe, maybe not. And maybe this, yes, in front of. So this is another mistake. I'm not sure that I can fix this. So I am telling you what the state is here, so I can then calculate the two Z's on it. And then I want to say, well, let's resume. But this thing, the red, is supposed to be right in front of the control Z. And then that's the reason, that's the right way. I'm sorry. Then the Z, control Z, could be with an arrow to the right or arrow to the left. It doesn't make any difference, as we discussed about a week ago. And so it produces this, which is really just this. And you know that if you have two superpositions of black and white and you feed them into two Hadamard gates, you recover the initial whites. And that's really what's happening over here. In addition, though, we said it's important to understand that for the things that are coming up, all this ability to calculate, you have to be careful, you have to practice, but it's a simple system. Basically, will need to be done, we will find a place where the circuit is very, very small. And the calculations that we are doing them now are not going to be correct. So I actually say, first of all, we're done with Grover. We have the circuit, we have circuit in slices, and we have calculations. And this new slides, I guess the only mistakes that I have is that I put a red dotted line at some point, a level before. But what I'm gonna do right now is I'm going to go to Curious for Quantum, the website, and I'm gonna remind you that he makes a statement which we have to be paying attention to because it's going to affect the reputation, and we're doing superdesk coding. Superdesk coding is still fine without any kind of modifications to the missing state formalism. But then for teleportation, we have to take into account what I want to emphasize now. And I go into supplementary material, and then I'm gonna go and say, this is a note in which we cover the standard quantum mathematical formalism, and I'm gonna come back over here, and he says, there is one subtlety, this one here, so right here, from there, all the way to here. He says you have to be very careful in the misty state formalism. We can only incorporate boxes whose representation is through a matrix, which is proportional to a matrix of integer entries. So I would like to understand if this particular circuit that I have over here is giving me trouble. Will it give me trouble or not? And so I'm going to reproduce it. And as I said to you in March, it was giving me trouble in 2 different ways. And if that's still the case, because we have new ways, thanks to Elmar, we have new ways of doing stuff, then if it's still a shortcoming of Qiskit, then we have to be ready to calculate that by hand. So I install Qiskit and this, before I go into superdense coding, it will present no problems, except I'm going to challenge you to read the material with a regular formalism and then go to the booklet and calculate it with the missing state formalism and then conclude that they are similar, if that's the conclusion that you're going to come up with. So before we do that, I'm going to come here and establish whether this circuit, or even less, this one particular gate has a matrix of the kind Terry said you have to have, otherwise it cannot be used in the missing state formalism. So then I'm going to say, for example, that I install what I have to install, and then I'm importing these packages. But now my circuit is going to be much simpler. And my setup here, remember that this is a class and it's supposed to be with quizzes and exams and midterm, final, right, in general. So I could easily say, somebody come over here, say everybody's in the room, say, oh, okay, how about you do this? I'll tell you what I need and you do it. And people would then look back in their notes and notes online, and instead of me just doing this all the time, we should take turns. In fact, we could in principle, but we don't have time to seriously right now. I could say somebody online, share the screen, how about you do it and we just ask for something, and that would slow down the lecture, but we will be sure that at least somebody is in fact able to do it as we speak. Okay, so I'm modeling that right now though, because we are kind of a little bit behind the schedule. So I'm going to say I did this, and I'm going to get the module for plotting if I want to see the circuit. And the very first thing that I'm going to do is something simple that I know. This is my circuit, but I'm going to make it super small. In fact, I'm going to make it empty. If I make it empty, my question is, how do I ask for this my circuit? And the only thing that it has is nothing. Good, let's draw it. Okay, what is the matrix associated with this circuit? It has to be the identity matrix. How do we generate matrices with the new Elmar rule? I'm going to go and say C290, and I'm just going to go 716 with the operator thing. Yeah, so I'm going to go and say, I forgot where you were telling us, but I looked at it before I left.
Qiskit top quantum info.
I'm going to go with 8. 8 doesn't have it, but I'm going to go with 9. And this is what I said we should pay attention to. Then the selection, then I think we have Elma saying, this is a better strategy. Okay, there's a better strategy. Then what do? I say from Qiskit quantum info import operator. This is a picture, so I can't copy. I'm going to say that from Qiskit quantum info import operator, which goes right here. And I say, there you go. Hopefully everything goes well.
Then operator that from something and QC.
So correct. So now I need to say operator from circuit. Operator from circuit. So I'm gonna come back here and say operator from circuit and then. Now I need the circuit. At the time, we used to have actual functions, but there's no function, it's just a variable A. So when I were to do this, it says I'm an operator. Oh, look at it. It looks good, doesn't it? It's the unit, it's the two qubits, that's 4x4 matrix, identity matrix, but we don't like it, right? We say draw. Output equals. Love it. Now we get a good looking matrix, hopefully. And that's the matrix. So we say, excellent. We have what we need. What if we introduce now a control knot? Just for this, for the fun of it, I come back over here and I say, here's a control knot. CX01. We have the same issue. I'm a little bit worried about that. Am I going to get the matrix that I want, or am I going to have to reflect the circuit to get a matrix that I want? So I'm going to say, whatever, this is going to put the control on the top. Well, that's how I draw it normally. Then I expect a certain matrix, I'm going to get it shuffled. So I don't need to import that, by the way, but here's the thing, that's not the matrix that I expect. So when I come back here and I'm going to say, why don't I get the matrix that people told me I should get? Because, you know, we read things and draw things differently than we actually have them recorded by Qiskit. Then I have to jump over this because, okay, fine, I will do it. And then draw this, and this is the matrix that we all remember. You say, well, how do we remember this? And what I'm going to do is I'm going to go here, I'm going to go on the what's new, and I'm going to click on matrices, find matrices. And this is where all the matrices are from Wikipedia. So I'm expecting this matrix only. See, that's what people do on paper with pencil. And then Qiskit does it slightly different. So remember this simple rule: if you have a circuit that you work out on paper in any formalism, MISTI or math or whatever, then when you put it into, I mean, you will match this in the books. And then you put it in Qiskit, you reflect the circuit to get the same behavior in the same matrix. So I'm happy, look at this. And a student could say, sure, you've used in this book, Terry's book, a lot of control knots and Hadamard. And they could say control Hadamard just by mistake. Okay, then my request right now is something we haven't done in this class yet, but we need to know the answer. I'm going to say the control should be a Hadamard. And actually, I'm going to put it, that's the right way. Remember, that's the way it shows up in my little circuit. So I want to control Hadamard. There is such a gate. Okay, great. So now I'm going to say, I don't have time for Terry's notes, right? I'm a student. I'm so excited. It looks like I can do everything with this. And then I'm running the operator. And I want to see the matrix. And now the thing is, does this match? Well, first of all, this is great. I wasn't able to get this in March. It said, I don't know what you're asking for. Yeah. So then I'm coming over here and I say, where's my little thing that we were working with? I have no idea right now, but I'm going to go into that in a second. The little qubit said, come on, because we have something in there. So do I get the same matrix? And if not, where's the difference? And I think we don't, because I think I calculate the matrix for the Hadamard plus the control Hadamard. And it would be much better, I don't know, we'll see in a second. It would be much better to say, I don't need a Hadamard plus the control Hadamard. All I need is control Hadamard. You can't get that in. And then you're going to say, why do you even need it? And so I was looking for the simplest possible example of a useful circuit that basically can't be handled by the system. And I found it in Watrous. Watrous says, is a state of entanglement that is not used as much as the GAZ or the Bell state, but still very important. I want you guys to know it. And I said, any student who has understood what we've done so far will go into Watrous and say, I want that. I want to do it. Because he says it's important to know it. And it turns out as follows. How about this? Remember Wolfram? I'm going to say Wolfram W entangled states. So I have to post some links. Wolfram, I didn't say Wolfram, but Wolfram doesn't have anything to do with W entangled. It's just W from, I forgot the name. And if you click here, this is the situation. This is the situation that I was trying to emulate. And I said, now I'm supposed to calculate everything with a mistake formalism until I find some short example that actually fails.
But this has a rotation gate and
Correct. You're going to say replay preview.
Really?
Okay. So here's the problem here. I was looking to, I have two questions from, we were invited with a tutorial. Last year at IEEE Quantum Week, and then this year, we also have one paper. And as I said, for next week, I'm going to prepare a draft to share with everybody to ask if people would like to be co-authors or otherwise involved in the paper. That would be outstanding. And the goal is to present this whole undertaking, this whole experience, and to establish either some opinions. At this point, we can only have opinions, but they are informed opinions, and a plan on how we could test this in, say, in 1 year or whatever, in the classroom for the sake of creating something that's sustainable, a faculty learning community for high school teachers in Indiana, and maybe elsewhere in the US, but in such a way that we could impact the curriculum for high school so that it would contain quantum topics presented, I think, through quantum computation. Because if you go through physics, it's just going to be too much. I don't know, perhaps the physics of it cannot be eliminated completely on account that it's what gave us quantum computation. And also there are some experiments that could be done, as we were shown in Canada at the University of Waterloo at Institute of Quantum Computation, to demonstrate the phenomena rather before you even do any kind of quantum computation. So I'm going to ask next week when we have the last meetings, is anybody interested? How can we have at this stage, at the end of these 6 weeks, a measure of potential success with the faculty learning community and with using these materials in the classroom within the next year, to basically apply some sort of plan to make sure that we make an impact, if that's something that people would be willing to try. And so hopefully this will continue to be sponsored next year by the Center for Quantum Technologies, except it would be very good if we had this paper, which paper has been accepted. It currently is a paper by me and Christian. So I'd like to have 8, 9, 10 co-authors, which will basically say what they think about what they've learned and how this could in fact impact the classroom in high school. As I said, there are 3 aspects that we need to work on. That is, provide materials for high school teachers, provide the ability to develop themselves professionally, and then make sure that we are reaching out and try to impact the actual curriculum. So we had some success at a higher level. We managed to impact the computer science curriculum, and I'll demonstrate this and I'll write down in the paper as well. At the international level, and I suppose that community much bigger, so therefore it was potentially more open, but we would like to come back to high school and say in the US, in Indiana, to follow the examples of Ohio and Texas. And that's the point. So if we were to go over there, we have this information and we present, and the CQT would be happy in November when they meet in Bloomington, and hopefully this will be at an even higher level next year. So you look at this thing, and last year in our tutorial, we had 2 questions. They liked it, but then they asked, how are you going to deal with arbitrary qubits, which we already had done? And I said it's in the teleportation example in the paper that will be presented. That was in October in Texas. And then they said, what about rotations? And we only had phases, right? Like 1/8 degrees or pi, if you want. So this one is an excellent example. And I have to give you a link to the Watros video that says why this is a meaningful state. The one thing that I don't understand here is where exactly is my example? This one is a better example, which is showing you what's happening through the state. So we calculate Bell states, we calculate GAC states, and now here's another entangled state that we could calculate. And I said, it's excellent that this is here, because I'm going to do it with MISTY states. It turns out you can't. On account, first of all, rotations, but then you can include rotations as arbitrary primitives, so to speak. And then we have our, I guess, culprit or element of progress over here, the control Hadamard. I say a student can easily say control Hadamard. I saw this in Terry's book because it has a lot of Hadamards and it has a lot of control knots. So you could just say at first sight, control Hadamard, just by mistake. And the result is, as I'm going to go into the syllabus to clarify, I know people have started calculating this. I've seen at least Christina calculating it and follow the steps to see that the thing comes up. If you don't have any kind of coefficients, you come up with the idea that there are 3 possible outcomes, each one equally likely. That's not the case. There are 4, but 2 of them are identical, which means that one of them is in fact 1 over square root of 2, the probability amplitude, and the other one is 1 over 2, 1 over 2, the other 2. And so I said that for the first time, the symmetry that's always everywhere in Terry's system is broken because of this. And if I go into this guy over here, let's see if the matrix that I have in here is the same as the one I just calculated with help from Elmar. So I'm going to say break even. What do I want to do? What I would like to do is to calculate, this is the circuit. And it comes up, as I said, 1 over square root of 2, and then the other ones are 1 over 2, 1 over 2. So the probabilities are going to be half and 2/4. That's overall is a 1. You calculate incorrectly, but that's how we know so far. And what's happening over here, you have to accept that this one here, the white, is already covering half the cases, but you lose that information if you just start unraveling things. Then you think it's just a third. So as I come up over here, here's what's happening. You see, I said, this is the, oh, I got it. This is in fact the controlled Hadamard gate calculated by me by hand. So this one here is the combined thing. And this is the Hadamard gate. So I got the right matrix. Now you say, it doesn't look the same. Can you get it? Exactly.
It's 1 more.
Yeah, so if I do 0, 1, guess what? Now the circuit is upside down, and when I run this, I bet I'm going to get exactly my matrix. So it is possible to calculate by hand. This is it. I'm very happy that this confirms the. You can tell that I was not able to ask Qiskit to get an answer from Qiskit in March, because if I had had that answer, it would have been on this page. But because it wasn't possible for me to get this, I did it by hand. And now look at this matrix. This matrix has the property that you cannot take a factor out, maybe irrational, but you cannot take a factor out and be left with a matrix of integer entries. You can. As a result, this is not part of his formalism. So now, of course, if you were to talk, you had the luck to talk to Teddy, he would tell you how you could simulate this matrix differently with other matrices and gates in his system, because he has this infinite resource of ideas and know what. But we are trying to explain that if, let's say, Teddy's not available and you read a book and you are happy and fascinated with the book and you run into this by mistake, you too should be able to fix this. And the simplest fix is to say, I need to carry the probability amplitudes in the system. In fact, some people do this from the very beginning. And it will look kind of like this. You can't possibly write white, black anymore. Put a 1 over square root of 2 in front of it. And that means that it's normalized. So we ask for them to be normalized, and we say that there should be actual coefficients. If you had white, white, black, 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 you will write that 2 white, 3 black. Or you would normalize it by saying square root of 2 over 5 plus square root of 3 over 5, I believe it is. And then if you square them up, you're going to get a 5 over 5, which is a 1. So introduce coefficients. Okay, so far we had a little bit of a breakthrough in the sense that I am going to go to students and I'm going to click on group. And I'm going to say in week 5, besides what we did already, we had this thing that demonstrates the matrix for this circuit. I think it's the matrix that I have inside the. This is what Qiskit reports, right? Then I have to say that what I have, in fact, let me do a second circuit. When I did it by hand, what did I do? I bet that what I did was essentially to take this. Let's see, where's my circuit? Yeah, so here's what I did. I didn't take this. I took the control on the second line with the Hadamard on the first line, because that's my little example, smallest example. So I'm going to create a second circuit. And just stay true to what I said before, whatever I do calculate by hand is basically as a circuit that is reflected compared to what Qiskit gives me. And then if I want to reflect it, I will get the other matrix. I'm going to say let B be another circuit, which is different connectivity. So instead of 0, 1, it's going to have 1, 0. Come on, move. 0, and then I'm going to run it, and this is a new circuit, and I'm going to say, will you please come up with the matrix for this guy? And now this is I guess a better looking matrix where it's clear that we had a nothing on one side and the Hadamard on the other. This is even better looking and shows that this is a matrix that cannot possibly be supported by the Mrs. State format, but he told us from the beginning, he knew this. So I'm going to say file and then download. And so when we do teleportation, which could be tomorrow, we have to establish, okay, I'm going to say controlled Pete box. So when we do teleportation, we have to establish any possible qubit as input. And then whatever that is, I would like to send it elsewhere. Whatever the protocol is, I do not know the state. And there is a theorem that I have to link because I promised this yesterday by Vazirani. I'm going to show you where it is in case you want to look at it already. I'm going to go into C290 that says, you have an unknown state and you would like to share it with somebody, you have to be ready to give up on it. You will not be able to keep it as long as they receive it. So cloning is not possible. I'm going to come and go here, click and go to the playlist. I looked into the video.
As I'm in the midst of applying for residency right now, wish me luck, Grammarly has again been a lifesaver with my application in helping me write my personal statement and CV. Grammarly.
So, block.
Okay, so in this lecture, we'll talk about quantum teleportation. This may well remind some of you of Captain Kirk and his crew, but
it's important to understand that we are not teleporting mass, we are teleporting information. So this is a 5-minute video. Let me play 2 minutes that will show you how the demonstration of no cloning occurs. And at least you'll have this for tomorrow when we do the teleportation. Then we go back and do the super telescope.
I should point out that quantum teleportation is a very serious enterprise. Now, for those of you who are not yet convinced that quantum mechanics is a very strange theory, this may be the topic which finally convinces you. One last thing, in the process of studying quantum teleportation, we'll also be exercising our skill at designing simple quantum circuits. Okay, so here goes. So in this first video, I'll speak about a related topic, which is the no-cloning theorem. So what's the no-cloning theorem? So imagine that you have a quantum state. Let's say a quantum state of a single qubit psi, which is alpha 0 plus beta 1. So you have the single qubit. Now, suppose that you did not know what alpha and beta are, but you wanted to make a copy of this qubit. So somebody gives you another qubit, which is not in the state psi. Let's say it's in the state 0. And what you want to do is you want to operate on these two qubits, and you want to do something to them, and you want to get both qubits in the state psi. So you want to take this second qubit and you want to convert it so that it's in the state psi. How do you do this? Okay, so let's formalize this problem. So we are given a state psi, we're given a state 0. We want to apply some unitary transformation to them, and we want to get to the state psi, tensor psi. Okay, is there a unitary transformation that achieves this? Okay, so this is one simple way of formalizing this question. The no-cloning theorem tells us that there's no way of achieving this. So let's show that there's no such unitary transformation that achieves this output on that input. Now, the no-cloning theorem is actually very simple, because what do we want? Well, we want to say that we want some unitary transformation that maps alpha 0 plus beta 1 tensor 0. We want U to map this to alpha 0 plus beta 1 tensor alpha 0 plus beta 1. Okay, and we want to do this for all alpha beta, suitably normalized, of course. Well, here's the argument. So, of course, if it works for all alpha beta, it must work when alpha equal to 1, beta equal to 0. So 0, 0 must be mapped under U to 0, 0. And you must also map, so if beta equal to 1, so we have 1, 0, what must happen to this? Well, the second qubit must look like the first one, so it must copy this value, so it must get mapped to 1, 1. And now, of course, since U is a linear map, what does this tell us about where alpha 0 plus alpha 0, 0 plus beta 1, 0 gets mapped to? So alpha 0, 0 plus beta 1, 0 under U must get mapped to alpha times U of 0, 0 plus beta times U of 1, 0, which is alpha 0, 0 plus beta times 1, 1. But this is not the same thing as what we are looking for, which is a tensor product of alpha 0 and beta 1 with itself. Because this is just alpha squared 0, 0 plus alpha beta 0, 1 plus alpha beta 1, 0 plus beta squared 1, 1. So the only way that these two could be equal is if alpha equal to 1 or if beta equal to 1. And so we have a contradiction. So we can't possibly clone an unknown quantum state.
And that's the argument. Where exactly am I going right now? All right, so I'm done with this, and I want to clarify that for that no cloning theorem to be presented in the Misty state formalism, we would need to have a place for alpha and beta to talk about qubits in general. So even for that, we would have to extend the Misty state formalism. Once we extend it, it would be a nice exercise to say, well, let's do it with Misty states. The idea behind this proof is that there is a matrix over there and it does a number of things. It's not that central. You could skip over that and instead just try to explain that once you calculate, you get these alpha square, alpha beta, whatever, and then you say, what are they? And you can't find a pair of values for alpha and beta, which are going to satisfy both equations. So it's just proof by reduction to contradiction. So I have introduced now the motivation, I guess the simplest possible motivation for extending the Misty state formalism. We'll have to do it for teleportation, but we do not need to do any of that yet because we have superdense coding. So now we have about 30 minutes to discuss superdense coding and see what we can do to present it and also see if we can follow it. So as I'm going down to superdense coding, which is like right here, I'm going to remind you that I said that there is a set of notes by Peter Shor that he's very well known for the Shor algorithm, but he has done lots of other things, including error correction codes. And I'm going to come and hit this, in which he says, if you were to start with these two statements, then you would say, I can't possibly communicate 2 bits of information over a line that uses a qubit. and a pair of entangled qubits. All right, so I'm scrolling down. This is a theorem. These are the drawings and so on. And now I'm going to ask myself, how can I prove to you that there is an, how do I prove to you what he hasn't proved? He says, we are not going to prove these things. We are going to refer to it later. Maybe later, he says, and he doesn't do it later. So, so I'm going to go and say, sorry, I'll go all the way to the end where I have the bibliography, and I'm going to look for Shor again. And so this is the link to that. All right. And he says these are two theorems, and no, not here. These are the two theorems, and we won't prove them now, perhaps in a later lecture. Now the question is, wouldn't it be great to actually prove them? Why not? And the question is, maybe we don't have time, maybe we don't know how to, but can we read them somewhere? And so one option for that would be just to clarify whether it's accessible to us or maybe not, or maybe it tells us what we should learn more to move ahead. I'm going to say, look at the press 29. I don't know that I said a clue, I put it here, but a clue to how you saw what Shor said he will prove later is here. Let me click on it. So it's in chapter 4. And here we are looking from some information that says that if you have an EPR pair, then it cannot possibly convey any information. So, you see that this is not only an entangled state, it's a maximally entangled state, which means that we need additional definitions to see what kind of degrees of entanglement we could possibly have. And this is one that we can easily produce with a Hadamard gate and a control knot. And as we go through this, I'm going to say that there is a place, I'll find it in a second, that says, what does it mean? What does it mean? Where is it? Where is it? I'm not sure where it is. Let me just search for it in a different way. So we know that if we have a pair of entangled qubits, the idea is that they cannot carry any information. So I'm going to say density. So first of all, it says the deep ways that quantum information differs from classical information involve the properties, implications, and uses of quantum entanglement. Recall from earlier sections that a state of two qubits that's pure is entangled if some property holds. Entangled states are interesting because they exhibit correlations that have no classical analog, and from Bettina, we know that they are called superluminal correlations. They are random but instantaneous. We will begin the study of these correlations in this chapter. Recall that they are maximally entangled if this property holds. And it says that when we trace over qubit B to find the density operator, we obtain a multiple of the identity operator. This means that if we measure spin A along any axis, the result is completely random, which means it cannot carry information. So in this statement, therefore, if we perform any local measurement of A or B, we acquire no information about the preparation of the state. Instead, we get a random bit. And this is what I think is an argument to prove those two, one of the two theorems from Shor. It still have the other one that says if you have a qubit, you can only send a bit of information. That sounds reasonable, right? Even though I don't have a proof. But here, if you say, how could an EPR pair not carry any information? Well, this is argument in one page from Preskill saying it's completely random. And this situation contrasts with the case of a single qubit in the pure state. There, we can start a bit by preparing, say, this and this. So now we have the argument for the first part too. This situation contrasts sharply with the case of a single qubit, but we can store a bit there by doing this and recovering it reliably by measuring over a particular axis. Good. We have some argument, all right? And so we come back over here and I say, what this tells us, what, not convinced?
I don't understand the notation with the arrow up that were there.
Correct, because we went straight in the middle of the lectures by Preskill. Okay. So if I were to go over here, this is chapter 4, where should I start? So the hat, where is the hat? That you say, what is the n hat over here? Is that the hat?
Arrow up and arrow down.
So,
But the arrows before the end.
before and, these are the spins.
Oh, it was at spins.
Yeah, spin up, spin down, but I don't know what N with the hat. N with the hat. So now we have to go, this is PH 229. And you come back over here. And you would go and say lecture notes, chapter 1. So I suspect that maybe, I don't know, we can go and find out what the hat might mean if we read carefully. See, which we won't do right now.
Maybe
But these are complete lectures, except that they're going far more and wider than what we need right now. So I gave you an example, like we jumped in the middle of Vazirani. That is kind of self-contained, it's good. But then if you jump into the notes from Prescott, he doesn't make them self-contained, this is a book. So if you accept that my quotes are supportive of the argument that Short presented without any proof, then good. And if not, that's all we can do for right now. So I'm gonna come back here and I'm gonna say, let me just go back to my thing. We need to understand how this works. And I have the following idea. I'm going to say, before I did this in the booklet, clearly things were already worked out somewhere. And I'd like us to try to read this. First of all, I gave you a proof by Vazirani that is using no missed state formalism. The question is, do you think you've been able to follow it? You could say, because 0, 0 is white, white, and 1, 0 is black, white, and so on. Okay, let's hope so. Now we're going to go and say, under what to do, I have a link here. And this is one possible argument or a test example. Do you think you can look at this and argue that you can understand? Here's another one. And where did it start? This one is the superdesk coding here. Let's go and read this one here. This is the one that I was looking for. So you're going to ask yourself, I'm supposed to do something, and let's say that I'm going to do by myself. I'm not going to wait for you to do it and post it and so on, which I will do anyway. But if you want to do it by yourself, you'll be able to actually copy, take information from this or not. So the very first thing that they are saying is that teleportation is going to allow you to move a qubit using 2 classical bits, whereas this one is transmitting 2 classical bits using 1 qubit. So it's a dual phenomenon. The process, you say, okay, in this process, I think I see where the circuit, how the circuit looks. I have to have some entanglement over here. And then I'm going to send this side to Alice and this side to Bob. Now, Alice is going to do something here, and she will have 4 possibilities. Now, this reminds you of Grover. I can put a queen over one of those 4 cases. Likewise, Alice can say, I'm going to send you 0, 0, 0, 1, 1, 0, 1, 1. Still 4 cases, but the purpose is different. The purpose is to show that if I choose this, now here, unlike in Grover, unlike in Deutsche, there's only 1 circuit, not 4 different circuits, no oracles either. This is a entanglement-based protocol, so the focus is totally different. And my question is, can I send Alice? Can Alice send 2 bits of information to Bob using this setup, which, as I said from Short, should be contradictory. No, you shouldn't be able to, because you have a qubit and then you have a pair of entangled qubits, so therefore there should be only 1 bit of information that you can send. And yet it is possible for her to set up her device so that if she presses 0, 0 or 0, 1 or 1, 0 or 1, 1, at this side, when Bob untangles everything, he will be able to tell which combination of 2 classical bits Alice said. And we're going to verify this. So the step over here is that you are going to, so as this put off everybody, we need to start in a certain state, and that's 0, 0. That's the state that we have over here. I guess it's difficult to follow, right? But then you say, I'm going to put a Hadamard plus a control knot, and the result is going to be after the first Hadamard. See, after the Hadamard, we get the state. So now, if we ever put the circuit together, when I slice it the way I did with Grover, these are the intermediary results. And you can say this is plus 0. We haven't seen anything like this, but you can tell that plus 0 is going to be 0, 0, 1, 0. That's going to be white, 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 black for us. And then you apply the C naught and you know exactly you're going to get the entangled state. Step number two. Step number two says the way Alice is going to communicate which one of the four cases she wants to send is by applying a gate, one of four, or a combination of gates, to what she receives. So we have this table. The table says if she applies nothing, then what she is sending, remember, we are talking about what's coming here and what she gets here that we sent to Bob. So there is an Alice on that line saying, I will do something so that when Bob receives the entangled qubit plus the thing that Alice has modified, then Bob says, I will recover that information. Notice that the Alice line has been modified by Alice in one of four different ways. And Bob should be able to get 0, 0, 1, 1, 0, 1, or 1, 0, exactly as Alice intended. So if Alice doesn't do anything, which means that she puts up an I, she receives 0, 0 plus 1, 1, she sends back 0, 0 plus 1, 1. Clearly, this is going to result back into 0, 0, but this table doesn't show it. Now, if you have, if she applies an X, then she's modifying her side of the state, and then that's what we should send to Bob to get the result. She has the option of calculating, of applying a Z instead, and then she has the option of applying first an X and then a Z. So you could say that these gates, all right, what is she doing? You know, thinking and then changing the circuit, she can't afford that. So she's going to have two gates, which are going to be controlled by the things that she's pressing. So she's going to press 1, 1. Both gates are going to be active. Now we have to Z and X in sequence. If she presses 1, 0, Z is active, but X is not. Remember, X is control not is going to have a 0 on the control, so it acts as an identity. If you want to apply just the X, then put 0, 1. That's the 0 that controls the Z. Therefore, Z doesn't appear over here. And then the 1 that controls X, which makes the control not act as a not. And then if you press 0, 0, both the Z and the X, which are there, are not participating. So now we have an idea of how the circuit is going to look. She doesn't modify the circuit as she decides what she's going to do. She simply presses the control buttons associated with the controls of the Z and the X gate. So as a result, we have calculations over here indicating that in the four cases that we listed over here, she's going to provide Bob with stuff that Bob's circuit, which is also hardwired over here, it's basically the untangling part of the Bell state circuit back into a control not and then a Hadamat, is going to produce by calculation either 0, 0 or 0, 1 or 1, 0 or 1, 1. You remember that the table that I'm showing you right now, where is it over here, is labeled 0, 0, 0, 1, 1, 0, 1, 1, and then the outcome that he gets is exactly 0, 0, 0, 1, 1, 0, 1, 1, meaning that the things that we have described are in fact going to participate the way we described to produce what she wanted to send. And now you say, I guess I could do this. And that's fair. Here's the circuit over here. And let's see if we can recognize this. The circuit that we have over here says, I am going to do one of four possible cases. So in this case, we assume that she really is coming with a circuit and putting in there because she wants to send 0, 1. All right. And in that case, this is a Z because she wants to send what? She wants to send 1, 0. But the circuit should really be the way it was described in the diagram over here. She's pressing some buttons and she's activating a Z gate or an X gate accordingly. So let's see what the other guy does, Macaulay, and come back over here. See, this is what he's doing, and this is a better looking picture. I'm going to have 2 bits, and my bits are going to be 0 or 1. I'm going to get those bits on the output exactly as I put over here. So if this is 0, 0, these 2 gates don't exist. Even though they are there, they're not active. They go in without any problem. You also notice how this circuit that you are looking at is not one of 4. It's all 4. because the input is going to tell us whether the thing is going to be or not active. So B1, B2 in reversed order is going to be listed over here, B1, B2. And for example, if they're both 1, 1, I'm going to get an X followed by a Z, and then the result is over here is going to be B1, B2. So this circuit is all 4, and the classical bits that Alice is trying to send will just control the bits, the gates that that she has. But she doesn't have 4 circuits. It's just that the input is going to cancel a gate or activate the gate. And now let's go back and see how I did it. I may have done it in 4 different cases, or maybe I have a circuit that includes exactly what I told you. So I'm going to click on supertext coding. Remember that this is a better looking circuit. This one here, sorry about it. And there's absolute benefit in this one too. The table was very good, and I'm going to scroll through this, and I'm going to say, I'd like to calculate. So I don't even have a circuit here. I simply calculate. So I'm going to do the following. I'm going to essentially start calculating, and I'm going to do that by saying stop sharing. So what are you supposed to do? I mean, I'm modeling what you should be doing, and I'll do it for you, and then I'll post it, and then that's it. I'm gonna stop.
Okay.
Oh, go ahead, because
I was just gonna say I had a question on the picture that was on the screen.
fine. Let's go back to the picture. Sure.
Okay. So I'm just thinking back to what Maria said yesterday about the 2 C knots kind of entangling and then unentangling.
That's correct.
So I'm noticing in the picture there are 2 C knots, but they're oriented the same way. Can you comment on that? My intuition is that the second one should be upside down, but I don't know why I think that.
Okay, they shouldn't be upside down. So remember, well, I'm not sure exactly if we said this or not. Any gate that represents any matrix, any quantum gate is in fact represented by a matrix. The matrices that represent the gates are basically unitary, which means they have a very specific property. They are their own inverses. So if I am going to do the following, you have the following question, and I think that's excellent, right? We should question everything, including whatever might be obvious to other people. Who cares what they think? We have to be sure. So I'm going to say stop sharing, and I'm going to come back here and say share content, screen, and I'm going to start drawing. So the first thing is perfect. Goal is to establish why exactly. Okay, I'm going to say this guy come back, and I would like to do what? I'm going to click on this, and then make this big, and take the eraser. Come on, eraser. No. Eraser. Object eraser. So I'm going to erase all of this to talk about this. Is what I did yesterday when I posted. So here's the first question. What if she wants to send 0, 0? Well, then the protocol says don't do anything. At that point, the circuit becomes exactly what Christina is asking about. So we're going to do the first case. Now she says they are oriented incorrectly. At least it looks that way to her. So let's first see if they are oriented correctly, and then what the other orientation might do. Now, I said to you that every single gate has a matrix underneath, and they have a following property that if you take the matrix and multiply with itself, you're going to get the identity. So I think I'm finished with this, and I'm going to come here and I'm going to cut the video and get rid of this one. And so it all starts. So here's what I'm going to do. I don't have a circuit in my booklet. And I said there should not be more than one thing. And then Macaulay has the right idea. There must be 2 inputs representing the controls of the 2 gates that will then activate them or deactivate them, so that whatever we press there comes out in the output. So a circuit will have 4 possible inputs, but it's the same circuit. So the question that we have right now, that we are trying to solve right now, is this is the pen, this is black, and I'm going to say I know the Hadamard gate. Well, I don't want that here. Come on. This is what I want. And then. I'm looking at a Hadamard gate, come on. This is a gate. I'm not sure exactly why it doesn't want to work with me, but here's a Hadamard gate, so. I think Christina would say, I know how that works. I'm very happy because I'm gonna ask you, what if I put another Hadamard gate? She says, the first day of class said that if you do two Hadamards next to each other, then they will recover the original state. So what do you have in the beginning? White, black, doesn't matter because it comes back to you. Okay. So another thing that he did right even before that is if I put an X, that also does something. And if I put the X again, that restores whatever it was in the very beginning. Clearly, these two matrices are working in a totally different way, but they have the same outcome. So now I'm going to say, what if I do a control knot? Like so. Well, it has a property. I have no idea what the property is, but it's a matrix, it's a 4x4. So its purpose is to apply that matrix to the input. Fine. What if I apply the thing again? All right, so I'm doing this with any gate that you want. Because the matrix underneath is unitary, that means that the gate itself has a matrix which multiplied with itself cancels and becomes identity. So this here is just the wire, this is just the wire, here this is two wires that are empty. I just simplify them. It's true that the control knots next to each other are simplifying, but they still have two qubits, and it's simply the tensor product of two identity matrices that result in a bigger identity matrix. Now, one other thing that I showed you earlier is that if I have, let's say, this circuit, this also shows up in the this shows up in the booklet. So, for example, I say at some point, what do you think happens when I have these three gates next to each other? And in the booklet, it is presented as follows. I say, this is equal to what, right? And I say, well, you could in fact try to prove that it's something. First, guess what it might be, and then prove that it is that. But at the level that we had in that particular stage, we were not able to do much. We just have like a huge table of possibilities. It would be much better to use the Mrs. State formalism and feed some qubits, arbitrary qubits. And so I have on that page where I'm asking how to do this, I say, go back, finish chapter 12 and come back and prove with the extended Mrs. State formalism that it is in fact equal to the swap gate. So I know what this is. And at least I can say, well, see the part where I'm guessing, that's given. This would be this. This swap gate is going to be the one that says whatever qubit you have on the first line will end up on the second line. That is, the qubit on the second line doesn't travel, but it will now take the state of the qubit on the first line and the other way around. So this is my answer to the question, do you think that they are oriented incorrectly? I would say I would take this circuit and I would calculate it with matrices and with a Mrs. State formalism, like this, to verify that it is or isn't the wrong way. Okay, so what does this do? Oh, not the circuit, sorry. The circuit that I would like to take is this one. I'm going to write it here. I'm going to say that in the pictures that we had earlier, I get a 0 and the Hadamard gate, and then I have a control knot, and then I have to ask Christina a question in a second. So I have this control knot, and the first question would be, does anybody challenge this particular setup? Is it not clear that this setup is in fact producing an entangled state? That's one thing that we have to ask ourselves, and if we're not sure, we have to convince ourselves. Then I'm putting here a dotted line, and I say, whatever the outcome is, and I claim that it should be an entangled state, I want to include this here.
We cannot see what you try. What
No, you cannot see. You're the only one who cannot see. Everybody else can.
I'm blind.
No, it's not because you're blind. It's because I use the desktop for something else in the classroom here. So I'm going to put this over here. And so the question is, what does this do? And my answer is, this is obvious that these two guys will cancel each other. I thought I did red, but apparently I didn't. And it
Oh.
does, see, so those two cancel each other, but we just talked about them here, right here.
But you have a gate in between and the multiplications are
There is no
not,
gate in between. Where is the gate in between?
well, on the top wire you have Alice and. you
No, no, no,
can
no,
not
no.
do the multiplication.
Alice doesn't do anything right now. Remember, we said Alice doesn't press anything. She wants to communicate 0, 0.
Okay,
So if I am in
Okay.
fact sending a 0, 0,
yes.
the question is, remember I said, let's start with the simplest case. And Christina says, for the sake of our discussion, why don't we prove that this is not wrong? Because it looks wrong to me or whatever.
Yeah.
So
I
the
agree.
argument here is, do you remember that there's a matrix behind every gate and the gate has this property, or we call those unitary? So then that cancels, which means that this here is going to be the same thing as Hadamard, followed by Hadamard on a wire basically that is empty, which is clearly the case that this is going to be that. So we have proved that Alice can send a 0, 0 by doing nothing because those two control knots cancel each other. Now, the question that I wanted to ask Christina was, when she said that they are oriented the wrong way, Christina, did you mean that they are both oriented the wrong way, or did you expect one of them to be the other way?
No, initially I thought they would kind of inverse each other by one being oriented that way and one being essentially upside down, but your explanation makes perfect sense that they need to be, that they essentially cancel each other out.
Okay, yeah, I agree with you, because I mean, because that's my explanation and I agree with it too, but I mean, that's just artifact, but what I want to say is, let's suppose that I suddenly challenge myself. I mean, maybe we'll discover something interesting, or maybe you're right, or, you know, or maybe I don't remember well and I'm just in love with my own explanation or whatever. So then, just for the sake of the discussion, which we're not going to do over here, I would take this and say, what does that give me? Just to see what's happening. And if I cannot recover 0, 0, then I will have to conclude all the things that we said are true, and we may have remembered things incorrectly or something. So I would still try this to see. Try this. Okay, so essentially we are now at 10:03, which means that we have to finish. What I will promise for tomorrow is that I will work out a circuit that combines all four that could be tested in any of the four cases. I also think that tomorrow we can go over, if you want, or I could write it down as slides. What are the four possible cases which actually I'm going to, how do I zoom here? Not this one, hang on, this one, and I say, well, where's the zoom? Zoom is here. And then I say, stop sharing. And we're just about to finish, but I would like to go back to the page that we had originally. Was the page? It's right here. And I'm gonna say, honestly, tomorrow I will have to describe and at least start teleportation. And in the process of finishing super dense coding, even if I write the slides and I set up a notebook and whatnot, I'll have to acknowledge the fact that these pages 40, 41, 42, they actually contain the calculations. They do the calculations on separate versions of the circuit. So it would be a nice, interesting approach for me to do for tomorrow, a circuit that results in this circuit, or the one with Z, or the one with XZ, or the one without X and Z, depending on the input that Alice is providing. But as it is right now, all the calculations are here, except that for every case, I build a circuit to show you that, that's what's happening. So we're done with super dense coding, at least in principle. This is a way to send more information than you could possibly hope. And I guess, I don't know, you could say channel capacity, super dense coding, and maybe you get some information. It's like in general, the channel can be as high as 2. So you don't have to send 1 qubit and then get 2 bits. If you send a number of, if you have a number of qubits, however many you have, then you can send twice as many bits over that channel. So that's why it's super dense, because you can squeeze a lot of information. Basically, for every qubit in this setup, you get 2 bits of information, which to start with in our simple setup already looks like some kind of surprising advantage. Good. So that's the end of today's lecture. Our goals now are to extend the Mr. State formalism and tackle teleportation. Okay, so thank you very much for your questions. I'm gonna say we have a chat, we have a bunch of participants. Anybody, any other questions? In that case, thank you so much, and I will see you tomorrow. I'm gonna post the recording a little bit later today, and then wrap up the slides and the circuit, as I said, and post it. Correct, I agree with that. So thank you. I'm gonna stop sharing, and then I'm going to stop recording, and then I'm gonna disconnect.